So at this point, I've done a number of different practice exams with different with different classes. So I don't know which ones I'm doing anymore to keep straight. We'll figure out what we're doing on Monday. I don't necessarily know if it will be exam review because we've gone over a lot of problems already. But I will get the location of your practice exam out to you in an announcement and an email. So, there will be that. On Monday, I might do things like introduce you to Linux or, and how to get that installed on your system if you want to. The basics of building a computer is something I can go into a 15-minute lecture on. So there's a lot of good questions. There's also going to be let's see. Let's see. So just making sure. Boom, 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 boom. Okay. So I'm just pulling up. So we went through the Harvard exam, I know, completely, right? And so we went through this one completely. But this one. And we didn't go through this. So I think I want to focus on this one and this one. Right? So some stuff from this one, and let me know if we've already done these because it's hard to keep it straight at this point. All right. So what organizational property obeyed by all nodes in a binary search tree, i.e. the binary search what is the organizational property obeyed by all nodes in a binary search tree, i.e. the binary search tree property? Basically, what is that definition of a binary search tree? Like, a set of nodes is a binary search tree if and only if you can select one node as the root, okay? You can set it into, you've got the root, and then you can take a remaining set of nodes and split it up into two sets. The left tree and the right tree, where every node in the left is less than the root and every node in the right is greater than the root. And that those two sets, the left and the right set, can be also separated as binary search trees, right? So in other words, a set of nodes is a collection of nodes is a binary search tree if and only if you can take a root, you get the root node, you can put all the stuff on the left that in a left set that's less than, all the stuff on the right side that's greater than, and then you can continue to apply that definition recursively. All right. So let the key of a node of a binary search tree be X. In other words, like the data stored in the binary search tree, let's call it X. Okay, and we'll also call the node X. Okay, so please keep the definition of predecessor of X. Now I've used that term before. It's not your parent what is your predecessor in a, sorry? Before is predecessor, right? So if you do an in-order traversal of the tree, then your predecessor is the node that comes right before you, right? Yes.
Oh, I was just going to try and answer.
Yeah.
You go left and you go right.
Yep, and that is the second part of the question. Given you are at node X and node X has two children, how do you find your predecessor of X by traversing your children, right? And the answer is you go one to the left and all the way to the right. I'm sorry, it's on one to the left on your screen and then all the way to the right. Okay, gotta remember that it's reversed from my perspective. One to the left, all the way to the right. All right. What about the successor of X? How would you find your successor, the node that comes right after you? Right. Your successor is your biggest is the smallest node that's larger than you, right? So in other words, the smallest node in your right subtree. So you go one to the right, and you go all the way to the left, right? All right. So why is it sometimes better to use a RedBlack tree or an AVL tree instead of your normal binary search tree? So RedBlack tree, that was a special type of tree that we briefly mentioned. What was special about it? What does it do?
Self-balance.
It self-balances. And ABL, again, I briefly mentioned, but it was in Chapter 9, which was on self-balancing binary search trees, so we can assume that an ABL is a self-balancing binary search tree. You typically, a professor will select, if they teach self-balancing binary search trees, they will select either RedBlack or ABL and basically focus heavily on one of them, right? So why is it sometimes better to use those than a regular binary search tree? I mean, the answer is in the name, right? They're self-balancing. What's important about that? So binary search trees don't self-balance. So what can happen in the worst case in the binary search tree? It just becomes a linked list, or it like zigs and zags in such a way that it takes O of n time to retrieve something. If it's self-balancing, that means it stays balanced, which means essentially the idea is that basically every time you make a branch to the left or the right, you're reducing your search space by approximately 50%, right? So that you can maintain that log n time. So creating some kind of ideal hash function and perfectly hashing stuff is not practical, and because we don't have infinite space, we don't have a perfect hash function that's going to work for everything. So let's talk about 3 ways we can handle collisions in the hash table. Okay, so there's 3 general schemes, right? So there's 2 general schemes that we learned about. I didn't go into any like third ones, but I'll talk about it. So when we get there. So there's 2 ways we learned about to handle collisions. What was one way? Chaining, right? That involved just basically, if there's a collision, well, we resolve that by having each index in our hash table hold more than one item, right? It's in fact what we do is that every item in our hash table, everything in our hash table is actually a linked list, and we store items in the linked lists, right? This is sometimes called bucket hashing, where each index is a bucket, and if you get hashed to that bucket, you just get thrown into that bucket. And then to find the item, you iterate through the bucket, which ideally is if our hash function is good, the buckets will be evenly distributed. So it'll take basically maybe only 3 steps to find a function. To find something in there. So chaining was the one I really didn't grade up, but that is one of the ways to do it. Hash table with chaining, right? So look something like this, right? Where basically things go into a linked list. If it's an empty table, we get it into the head of a linked list. Let's see if there's a good image of that. Right? Right. So you get collisions, and instead of looking for the next available space, we basically chain stuff together in a linked list. Speaking of looking for the next available space, what is that approach called? Open addressing, right? And we learned about 2 ways to do that, to do open addressing. The first way was linear probing, right? Which is what you'll be tested on the exam. So linear probing just means if you get a collision, what do? Go to next space. Well, there's a collision there. Next one after that. And so on and so forth until you find an empty space. You're guaranteed to find an empty space, by the way, because your hash table needs to resize in order to work, right? So your hash table should never be full, right? Because a hash table, the way it works quickly is by having plenty of extra space so that we can quickly find an empty space, right? We never want the parking deck to be full up so that it takes forever to find our car. Okay? So there's other kinds of things. There's weird kind of other ways to resolve collisions. One is I think Cuckoo hashing is one way, which I've never really learned, but it's a way to resolve collisions. The name derives from the behavior of some species of cuckoos, in which the cuckoo chick pushes other eggs or young out when it hatches. Analogously, when you enter a new key into the hash table, you push older keys somewhere else. So in other words, when you insert something into a hash table, you kick somebody out of the spot and move them somewhere else. So how does that work? That's just another general approach. The specifics are, a bit different. So hopscotch hashing. Well, perfect hashing. The ideal is that basically we've got a perfect hash function that maps everything, all of our inputs, into a unique index without any collisions, right? That's not always practical though, because if you're just trying to have a hash table that can take anything, like in Python, that doesn't seem too good. Now, like an example of a perfect hash function is that if we've got it would be basically if we have an array, okay, of that could hold all possible integers, a giant array that could hold all possible integers, and basically the input and our inputs are only all possible integers. And by all possible integers, I mean like Java integers, so the 32 bits. Obviously, so we can obviously map every guy to his own space. There. No problem. But continuing on. Okay, that's what I believe it's supposed to be. It could be wrong. All right. So we've got open addressing, and the other way to resolve open addressing we talked about was quadratic probing, where instead of looking you look 1 away, but if there's a collision, then you look 4 away from your initial spot, which is 2 squared. Then you look 9 away from your initial spot, which is 3 squared. Advantage is that that's more spread out. Disadvantage is that while it's more spread out, you have to do a multiplication operation in addition to doing an addition and a modulo operation. So it takes a bit longer. And if it's really full, it might take a while longer than a linear probing to find that empty spot. All right. Under what conditions would you prefer using an adjacency list over an adjacency matrix? Okay. Why would you want to use? So you want to use adjacency matrices when? Just to represent a graph. Dense graphs, right? Dense graphs. That means when there's a whole lot of edges. Okay, so adjacency lists are used on sparse graphs, right? So you want to use in a sparse graph, basically when there's only some when there's only collision. I would also consider using adjacency lists when I don't actually care about the nodes themselves, and all I care about is the edges, right? Because the adjacency list, I can just iterate through all the edges, no problem. Whereas with an adjacency matrix, if I have to iterate through all the edges, I have some wasted space. I have to basically check, does this edge exist? And there's no checking if this edge exists in an adjacency matrix. With an adjacency list, I can just simply say, this edge exists, go ahead and do it. This edge exists, go ahead and do that. All right. So, let's see.
The cutoff for when's better to use a matrix, is that like
25%, when 25% of all possible edges exist.
The possible edges with the nodes squared?
Yeah, okay. Right, because in a simple graph, right, you can only have one edge between any pair of nodes. Now, there's things called multigraphs where you can have two different routes two different edges between a node. Much like how, you can take, you might have a toll road between 2 points, right? And you can take that, and that's going to cost some amount of money, right? So we'll put that there. And then you have this one over here, but the cost instead is taking more time, right? We're getting stuck in a very constant traffic jam or something like that, okay? So, and typically you use the same units for weights, but, right? So I might put 0 over here, but, if you care about, money, then that's the way to go. But the graphs we deal with are simple graphs, for right now. All right, so that's a pre-order traversal, post-order traversal. I'll get back to that. I think that's a good one. We'll go over also the graph problem again in a bit. Yeah, let's start with this. Since we're on graphs, let's do graph problems first. All right, so here's a graph, and it's adjacency list representation. Now, you guys will be expected to take a adjacency matrix, right, and turn it into a graph. Okay, so we'll go ahead. So for those of you like myself who are not so visually inclined and good at plotting things out and actually have terrible handwriting, we've done you the favor of already putting the nodes on the exam, say here's your node, so you only have to draw the edges in between them, and we've drawn everything in such a way that basically it should be not a bunch of gobbledygook for an answer. But you're expected to be able to turn an adjacency matrix into like a visual representation. And that brings me to another point. If for some reason you cannot, I just need to mention this because students keep getting surprised by this. If you have more than 2 exams in the same day, you are allowed to ask professors that one of the professors is expected to make some kind of accommodation. Now, the professors may moan and complain and stuff about being the one who has to move, but one of those professors does have to move, and so what I'm saying is that basically, if you've got 3 exams, make sure that you do not actually have 3 exams on the same day. That's you're not supposed to do that. And for this one, if you have a conflict with if your common exam has a conflict with another exam, it's a pretty easy solution. You just come and take the evening exam. So if that happens, please see. So if you've got that conflict, please let me know as soon as possible so I can resolve that. Yes.
What time is the exam again?
Your exam is at 3:30. From 3:30 to 5:30. I don't know where it is. I just got the email today about where they're assigned, and I have to look up what the building code translates to. So the 3:30 to 5:30 on the 8th. It's not here though. It's not in this room. It's a common finals. Yes.
Is the 8th the last day of exams?
I think the 9th is. The 9th is the last day of exams. So 3:30 to 5:30. I will be in 2 places at once, like usual. I have, since I teach 1068 and 2168, and they both have the common final on the same day, it makes it a bit difficult. And then I'm also here from 5:45 to 7:45. I'll be here giving the final exam for 2168 evening session. So if for some reason you can't make it to the common final, arrange with me in advance. Okay? Again, a lot of the final issue, if you're having issues with finals, a lot of those kind of issues can be solved in advance if possible. If it's not something that gets solved in advance, it's like a hospitalization or something, then you need to get once you can actually communicate with me again, get me some documentation, right? All right, so let's go ahead and look at this right out the order in which the vertices in the graph would be visited if a breadth first search were started from node 3 in the given the above adjacency list representation. Note there's only one correct answer since you must use the given adjacency list and follow the rules of accessing such a data structure. That means normally if I were just giving you this graph, you could say, okay, I'm doing breadth first search, so I could visit 2, then I could do 1, then 2, then 5, or 2, then 1, then 5, or 5 and 1 and 2, right? I could do any of those things. But it's saying you need to go in the order of what's stored in the adjacency list. So, right? So we're going to go ahead and do our set of scene, our queue of stuff to visit. So our queue, and our list, which is an output, right? Right. This is now because the way that that me writing stuff on the board works. This is going to be identical to this, but that's okay, right? But you can do it with basically just 3 data structures. Okay. So breadth first search, we start at 3. Let's see. So we start at 3, and 3 is in the queue. So we need to dequeue our queue to find out where we currently are. Okay? So we're at 3, and we need to look at 3's neighbors. Have I seen 2 yet? No. Into the queue it goes. And I've seen it. Have I seen 5 yet? No. So into the queue it goes, and have I seen 1 yet? No. Into the queue it goes. Okay? So now I look at find 2's neighbors. 2's neighbors are 3 and 1. Or 1 and 3 rather, in that order. So we're done. DQ 5. What are 5's neighbors? 5's neighbors, right? And we need to do this in the order they said to do it in. Like for us, when we do something, we might say break ties alphabetically or something. That's generally the easiest way to do it. But let's see 5. 5's look at 6. Have we seen 6 yet? No, we have not. Throw it into the queue. What's the next neighbor for 5? 3. Thanks. We've seen 3 though, right? So no need for that. And what's the next thing for 5? 8. We have not seen 8, so throw it into the queue. Okay, so we saw 3, then 2, then 5. Now we DQ 1. Okay. What are 1's neighbors? Because I have 2. So 3, 2, 4. Have we seen 3? Yes. Have we seen 2? Yes. Have we seen 4? No. Into the queue it goes. Okay? Okay, now DQ 6. 3. Yeah. So it's 3, 2, 5, 1. Now we DQ 6. Okay, we're at 6. What are 6's neighbors?
4, 8, 5.
4, 8, 5. Seen them all. What are 8's neighbors?
7. Oh, I'm sorry. 7, 6, 5.
7, 6, 5? 7, 6, 5. So 7, 6, 5. I haven't seen 7 yet. Was 8's neighbor? Wait, was 7's neighbor? 8 have a neighbor of 7 when I DQ'd it? I think it did. Right? So let's back up a second, because I wasn't looking. I was relying on you guys. So let's back up to 8. So 8. So we had 6. We added 4. So 6. We added 8. 4 and 8. Right? Except that we added 8 when we had 5, right? 5, 8, 6. So 5 was the neighbor of 6 and 8. Okay, and then we did 6, and now we're at 8. DQ 8. 8 neighbor has 7, 6, and 5. So we add 7 here. Okay. Now we do 4, which is seen in here. And 4 has no neighbors that I've seen so far, and then 7 has no neighbors that I've seen so far. Right? Don't make a silly mistake. Be careful with those. Okay? So let's go ahead and start def for search instead. So def for search is going to work the same way. We've got a scene. We've got our output. Okay, the only difference is that we've got a stack S, and our output, does it want it in the visited order or in the finished order? So visited, meaning the order in which we actually enter stuff. Remember, the finished order would be the order we pop stuff out. So let's go forward with this. So the first thing we need to go and do is put 3 on our stack. Is 3? We peek at 3. Are we at a dead end? No, we are not. So now we need to choose one of 3's neighbors. Okay. So 3's first neighbor is 2, so we're going to choose that. We've seen it. Okay. What is 2's first? What is the first neighbor of 2? 1. 2's first neighbor is 1. Okay. What is 1's first neighbor? 3. Seen it. What's the next neighbor? 2. Seen it. What's the next neighbor? 4. So 1 has. Okay. So go to 4. What's the first neighbor of 4?
6.
Neighbor 4 is 6. Haven't seen it. What's the first neighbor of 6?
4.
4. I've seen that. What's the second neighbor of 6? 8. Okay. What's the first neighbor of 8? 7. First neighbor of 8 is 7. Haven't seen that yet. Okay. What's the first neighbor of 7? 8. Seen that. Does it have another neighbor? Nope. Pop. Okay. So what's the first neighbor of 8? 7. Seen it. What's the first neighbor of what's the second neighbor?
6.
Seen it. What's the next neighbor? 5. Haven't seen that. And then at this point, 5 doesn't have any neighbors that I haven't seen, so pop that off. Then 8, then 6, then 4, then 1, then 2, then 3. Right? We visited all the nodes, so we're at a dead end. Yes.
I'll think about that.
Okay. All right. So this question, I'll probably. So we have the right. Yes.
I was just wondering, on the test, would you want us to be writing out the full algorithm, or is it just we want us to?
What is the output essentially? And we'll typically ask you to stop at a certain point. That's how we are able to check to make sure you don't you know how to do the algorithm. Dijkstra's will be worth more So we'll make sure to do that again. Let's take a look at this problem, which is a problem that, yes,
Just back to the breadth.
yes.
Should we be concerned at all with time and space complexity? Because I don't know, I didn't actually think about it, but it seems like we're going to need to store more for depth research. Now we need to think about that kind of thing.
No, not for the exam. Depth first search and breadth first search, right? They have costs that we went over in the slides, but I'm not going to cover them on the exam. Okay. I do like to tell you try to tell you what's not going to be covered on the exam, so that you don't necessarily have to waste your time on it, because your time is limited for a final exam. On the exam 2, I might have given you a maybe, but on the final exam, okay. So, this one is one that you might get something like it on the test, because I think what we've been allowed is to change on the common final to change 1 or 2 problems into something more specific that we did in class. So this is a harder version of anything I would do. I'd probably do something similar to what you got what you got in if I did a hash table problem. I'd do something similar to what you got on exam 2. So here's a hash table problem, and it tells you. Now, mind you, they did it in C++, so it looks a little different, right? With the lowercase and that thing. But let's get into it. You're given a text file that contains a week's worth of login duration for users on aludra.usc.edu. Okay, so that's the server that they host. That they that's their Linux server, I'm assuming, right? Okay. So each line of the file corresponds to a single login session. So a line might contain the user's ID, for example, Cheng W, followed by the space character, followed by the user's login duration in seconds. So, for example, 3.14326. Your job is to compute and print out the average login duration for each user. E.g., add up all the durations for a user, divide by the number of login sessions, right? So compute the average number of sessions for each user. For example, if your input file has 2 sessions for Cheng W, one is at 3.1426 and the other is for 204.7, then Cheng 259.513 should appear in your output exactly once. So let me give a better example. So suppose our inputs are Alice. Suppose our file is Alice 5, so she was logged in for 5 units. I'll go with 50. So 50 seconds. Bob 20. Bob 30. Alice 100. Bob 40. Let's go with Carl 70. Okay, so say those are our inputs. Then our output, it says, because this is we're dealing with math out, and they've mentioned this in the problem, but the order that the output comes in doesn't really matter. So our output might be, to console, because that's what it's expecting. It's expecting us to output to console. It should look something like this: Bob 30, because on average Bob was logged in for 30 seconds, right? Right. The average is 20, 30, and 40 for Bob. The average of Bob's logins is 30 seconds, right? 20 plus 30 plus 40 divided by 3, right? When you've got 3 numbers that are spaced evenly apart and you ask for the average, it's the even number. Alice logged in twice for 50 seconds and 100 seconds, so that's 150 divided by 2, so Alice was there for 75 seconds on average, and Carl has only 1 input, so we output 70 divided by 1, which is 1. So that's our output. So we need to use maps for this problem. In fact, they enforce that on the problem, saying you need to use the STL, standard library, maps. And they tell you want one for the duration sum. In other words, the sum of how long everybody was logged in for, okay? And count, which is the which keeps track of the number of times each user was logged in. So this is a 2-part problem, which is why I kind of like going over it. It's the I feel like this would be a perfect timed lab problem for next semester for students who come in, because essentially give them a file, they have to read the file, break it up into the two component parts, and then use the maps. So, but we'll go over it on here, and we'll see that it is, while it's long, in fact, they give you plenty of space to do it, it's not hard. Okay, so the first thing we need to do is like read the input file, okay, line by line. Okay, and then once we're doing that, we can start throwing stuff into our data structure. So let's go ahead and type it up on. Do you want me to do it on the board or type it up? Type it up. Okay. So let's do a new file. All right. So I'm not gonna bother using syntax highlighting for this. Okay. Edit. Let's see, preferences, settings. Let's go ahead and bump up the text size so that it's nice and easy for everybody to read. So I'm just going to go ahead and assume we're in a function right now. So I would use scanner is equal to new scanner, and I'll assume that my input file is called input.txt, so new file input.txt, right? That makes sense. I'm just going to read this file. That's probably going to throw an exception in a real problem, whatever, right? I'll need to put that in a try-catch block, but again, whatever. So now to read everything in the file, while scanner.has next line. So while there's still stuff to read, I need to read it. String line is equal to scanner.next line. Now, so I'm reading every line now, so that's good. Now I actually have to do something with that line. The line has two components to it, right? It has the login portion, and then it has the numeric portion. And it said that they were separated by a space. So in that case, I'm going to use the split function. So string array parts. I'm going to basically be as simple as I can with this. String array parts, I'm going to split it up into two parts, is equal to a line dot split. So now we have two parts to this, and we got to tell it how we're splitting. We're splitting across that space, that single space that it says that I can assume is there. Okay, so now index 0 for parts will be the login name. So string login is equal to parts 0. Okay. And then the second part is the login time, which is a double. So double time is equal to parts 1, but I need a part, but that's a string, so I need to convert it to a double. So double dot parse double, like that. Okay, so now I've now got broken up into the login and the time, which are essentially going to be my keys and values, right? The time that I log, so we've got two maps. So one map counts the duration. The key is the user who logged in. The duration is the sum of the amount of time he logged in for. So that's the duration map. The count map is its key is the user who logged in, and the value is the number of times she logged into the server. Okay, so we've got that, and we've got the I'll call the duration portion the duration map sum. So we'll call that actually I'll just call it durations. So durations. So first thing we need to do is essentially check durations. So first off, does the durations does the durations map contain the key, contain this user? Right? Does it have this person in it? And so if it does, do one thing. If it doesn't, do another thing. And the way we're going to be constructing this is that we can assume that if the person's in the durations key, if the person's already logged in, we've seen this person log in before. if they're in the durations, then they're also going to be in the count. So we don't need to do 2 checks. Right? We don't need to do 2 checks. So let's go ahead with the else, the initialization. So if it's not already in there, durations.put login, and then the amount of time they've spent there, and then count.put login, and we've seen them once. Okay? Otherwise, if we've seen them before, then we want to put in for that person the amount of time that they just logged in for, plus the amount of time they've already been there. So I'm going to actually kind of do a weird nested call. Get. So get the amount of time this person's already been logged in for, and then add it to the amount of time, right? And add that to the amount of time I just saw them log in for. And then similar over here, count.put for this person that they logged in an additional time. And to do that, we have to do count.get. And we could break this up into multiple lines, but I'm being efficient with the space here, like the physical space on my keyboard, on my screen. Okay. So now we've got the counts, we've got the durations. Now we can average everything together. So we've done reading the lines, we've populated it. So so let's see, for string user in, let's see, durations dot, I think, what is it, get key set, right? I'm going to look it up because you should have, you'll have a cheat sheet. So map API Java, right? So don't have to look at the hash map, I just have to look at this. So key set. So for every key in the key set, durations.key set. So for every user in our keys, system.out.println that user plus, now I need to know how, I need to know how long they were, the average of the time they were logged in for, which would be durations.get user divided by count.get user, .get user. Right? And that's all you need to get to output to output everything. Let's try turning it down to maybe 18. Okay, so that's the answer to that question. All right. So let's see. That's not something we'll test you on, so let's go ahead and on to this one. All right, did I go over this question already? Asking about insertion sort and merge sort, right? So let's look at insertion sort versus merge sort. Have I asked this question before? For each algorithm, what is the worst asymptotic upper bound for on the running time that if you know that the input is sorted, reverse sorted, or just a list that has n copies of the same number? Did we go over this problem yet? Okay, so let me rephrase this one for you. Let's look at both insertion sort and merge sort. For that algorithm, we want to know, in the worst case, how does insertion sort perform if your input's already sorted, if your input is reverse sorted, so in other words, it's sorted from not less to biggest, but biggest to less, and we need to arrange it in from least to greatest. And then C, which is something we didn't go over, but we should be able to figure out, what if it's a list that has n copies of the same number? Okay, so let's look at insertion sort first. How does insertion sort perform if on the worst case, if it's already sorted? Right, the worst case is O of n squared in general, right, for any arbitrary input. But what if the input's already sorted? what will we expect insertion sort to do? It's going to look at the first item and like that's automatically sorted. The second item, well, that's already sorted too, so it just tacks it on. The third item's already sorted, so it just tacks it on, and so on and so forth. So what's the runtime of that? O of n, right? If the input is reverse sorted, how do we expect this is going to perform? It's going to be n squared, right? Because the first item has to be sorted, is sorted, but then the second item we have to push down into sorted order. The next item we have to push 2 down, and then the next item we have to push 3 down, and the next time we have to push 4 down, and so on and so forth. What if it's a copy of, what if a list is just, it's size n, and there's n 3s in there, right? So it's just a list of 3s. How would that perform? So the question is, it's how we handle numbers that are the same, right? And so what?
Would it be the same as already sorted?
Yeah, be the same as already sorted if we consider numbers to be, it should be the same as already sorted. Remember, insertion sort's what we call a stable sort, which means that if we've got basically, which means if we have like the king of hearts come before the king of diamonds, then our output will have the king of hearts and the king of diamonds. If, so basically two different values, assuming that the king of the hearts and king of diamonds have the same sorted value. Okay. Now for merge sort, how will merge sort perform if it's already sorted? So merge sort, it's going to break it in half, right? And then it's going to break those halves into halves, and then those halves into halves, and then merge them together. So what's the runtime for that? Sorry, not log n. Log n is the breaking, how many times we're going to break it in half, right? And then each time, n log n, right? It's n log n because we break them in half. We break it in half log n times, and then each time we break it in half, we have to merge those halves together, which takes O of n time. So we have O of n merge. Sorry, we have log n merge operations, which take O of n time each. What is reverse sorted? Same deal. The nice thing about merge sort is that it is consistent, which gives us the answer for C, which is that it will perform exactly the same. It always performs n log n. Disadvantage of merge sort is that if you're using arrays, you gotta have more space, right? Linked list, you can probably code it up so that basically you don't need any extra space since you're just moving around pointers, but at the same time, you're probably going to have some difficulty like finding the middle in your linked list and stuff like that. So, let's see. So, let's see. It's another one. All right. So this is another one I like. So suppose we have a hash function, and we've inserted some elements into a hash table. We've got a hash table, and we've inserted some elements. Let's inspect it, and we look at it, and the result of inserting a bunch of stuff looks like this picture over here. Okay. Being a good student, you realize there's a problem with this hash table. Now, obviously, this is a hash table with chaining as opposed to doing open addressing. So 3 questions. We'll take them one at a time. What's the problem? It doesn't have to be specific. Really, you don't have to. You don't have to be too technical about it. What is the problem with this?
It's not evenly distributed.
Not evenly distributed. I would also take in the non-technical things aren't spread out. It's not evenly distributed, right? We've got the numbers really clumped together with a bunch of gaps. Okay. So, and if things aren't evenly distributed like this, it can often be a problem with the hash function, right? You probably have a problem with the hash function. So part B is, and I want you to take 3 minutes to think about this one. Let's figure out an example of a hash function, right? Some function, h of x, right? That's given an x as your key, would output this. So in other words, try to construct a function that would output this. What hash function would result in 0 and 30 going into index 0, 21, 31, and 1 going into 2, and so on and so forth. Trying to figure out a good hash function that would do that. So you've got about 3 minutes. And I'm going to take the time to just look at my phone. Right? Look, if you haven't figured anything out yet, look for some kind of pattern. Right? What's in common? So if items are ending up in the same bucket, what is the commonality between those items? All right, any takers? Okay, go ahead.
Your last digit is the same, and it's twice the index digit.
Right. So you put it in. So basically everything goes into the bucket that is twice its last digit. So we can reconstruct our hash function as. Do you have a suggestion?
Well, yeah, I had the hash function if you want me to just say it.
Yeah.
Just let's see, x mod 10 times 2.
Yeah, x mod 10 times 2 will give us this. So part 3 is construct a better hash function than this, right? Now, why is this one terrible? Well, because we're not using any of the even square, we're not using any of the odd buckets, right? Because of this, we're modding something and then we're not using any of the even buckets, right? Removing the times 2 doesn't do any better, but we have 20 spaces over here. So even the most basic of hash functions, which is to take the key and mod by the table size, that will do better for a lot of stuff. Ideally, though, if you want it to be more distributed, you want a prime number of spaces in here, which maybe you might want to increase the table size to 23 or something like that. All right. So, suppose we have numbers 1 to 100 in a binary search tree, and we want to search for the number 45. Which possibly multiple following sequences could be the sequence of nodes that are examined? In other words, we're iterating. These are possible trees that we could iterate through. Which of them are actually possible? So we want to look for 45. So we visit the root node first. Then we go to 2. Well, that's not going to be possible because we'd want to go to look for something that was greater. Right? If we're looking for 45, then we want to go greater. So the next node we wouldn't want to visit 2 next, right? Right? 40. So if we visit, the first node is always going to be the root of the tree, right? Right? And the numbers are 1 to 100 stored in a binary search tree. So if we look at 5 and we go to the right and we hit 2, that's not going to help, right? So 1, we go to the right, we hit 2. We go to the right, we hit 3. We go to the right, we hit 4, and so on and so forth until we hit 8, right? So then we can, and then so on and so forth. But this is a good, this is fine. We keep going to the right. We keep going and finding a bigger number. 9, 8, going to the left, then 63, no. Again, we went we need to go to the right. Right? We've got to find a number bigger than 9. 8, 7, 6, 5, that's going smaller, so that's not going to work. 50. We need a number smaller than 50, so we go to 25. We need a number bigger than 25. 26, 27, 40, 42, 42. That's not going to work because that 42 is smaller. But this next one is fine because it's missing the 42. You could go to the next node and everybody see how that kind of works? Okay. This is another good theoretical question, but I don't think it's worth 10 points. So suppose we first insert an element x into a binary search tree that does not already contain x. So in other words, there's no copy. So say we're inserting 3. 3 does not currently exist in the binary search tree, but now we put it in. So we put it in, and now we immediately delete 3. Will the new tree be identical to the original one? If yes, give a reason in no more than 3 sentences. If no, give a counterexample. So what happens? So where do nodes go when we add it to a binary search tree? Where does a node go? Yes.
It becomes a leaf node.
It becomes a leaf node. It always gets added straight to the bottom unless there's a duplicate of it, but there's not in this case because it said so. Right? It goes straight to the bottom. Okay. So now we've added a node straight to the bottom. Now we delete it. Is deleting hard when we delete the last node? Nope. Does it affect the structure of the tree at all? No. So it would be identical to the original one, unless unless your argument is that like the ship of Theseus as parts get replaced is no longer the exact same original ship. Now the only counterexample I can say is that if it was a self-balancing binary search tree, right? If you add a node and now it's unbalanced and you rotate it a couple times and then you delete it, right? In that case, you would be modifying the structure of the tree, but I don't think that's what it's asking for. All right. So suppose we have a graph like the one below. The dots signify some part of the graph that you don't know exactly, but not a straight link. You also know, however, that there's many paths from the start to the goal. You also know that they tend to be rather long. Suppose you want to implement a program that searches for a path and returns the first one it finds. You have no need of finding the optimal path in any sense, just any path will do. Do you want to use depth first search or breadth first search as the basis of your program? Justify your answer in at most 2 sentences. Now, we had a discussion about this problem last night, and I accept either answer with proper justification. It's the justification that's the hard one. And how you and it all depends on what you assume this problem means, what this diagram means. So anyone want to take a shot? Yeah.
I would choose depth first search.
Okay. Why?
I mean, in that picture, I'd be assuming that most start paths have a goal path, and you'd be able to find the path to the goal by traversing the least number of nodes with depth first search.
Right. That's a reasonable assumption because this seems to imply that basically this arrow going here, you're not hitting another node and that those nodes don't have branches, right? That's kind of what this picture implies, that the start node and is the only one with branches, right? That's kind of what this implies. So if you're looking at no branches, like you're not in a kind of maze setting, and you're like saying any one of these corridors will do. Some of them will have dead ends. Some of them will get me to my goal. That's perfectly fine. Okay. Now when I saw this problem, I'm biased towards breadth first search, but that's because of my research. Now, but everybody understand under what assumptions depth first search is going to work and what other ones, and under a kind of a maze circumstance, it would be terrible, right? So I'm biased towards breadth first search because of my research, right? Because the assumption here is that you'd have branches. And when I see this diagram, I assume what's called a small world network. Anybody know what I mean by that? Nope. Okay, so let's see. So the idea was that like with a small world network, right? Everybody knows the idea of 6 degrees of separation, right? Right. you got some person, right? You've got some person over here, and then you basically got, you know, a connection to this person, and then this person, and then this random other person in a country you never heard of, right? You can draw a connection between you and them, just like with at most like 6 steps. Is kind of the idea.
We talked about this with Kevin Bacon.
Kevin Bacon, yes. But where does it come from? Anybody know? All right. So who knows about Stanley Milgram? Anybody? Anybody taking psychology? It's worth it to take psychology. Yes.
The letters and stuff.
The letters? Yeah. Yeah. Stanley Milgram set out those letters. But what else is Stanley Milgram known for? Just anybody happen to know that one?
The doctor experiment.
The shock experiment, the shock obedience experiment. Now do people know? How many more people know what I'm talking about now? Half the class. For those of you who don't, so the idea here is that in the 50s, I believe it was, let's see, Israel managed to capture Adolf Eichmann. Anybody know who he is? He's one of the bastards that murdered half my family. So he was one of the main perpetrators of the Holocaust. And you know, he was brought to Israel, and he was on trial. And you know, the typical defense of Nazis is, I was just following orders. And so the question that Milgram asked was, well, I'm a psychologist. Can I test, do people follow orders, you know, even if it's going to like harm or kill somebody? And so he just constructed an experiment. Essentially, he put out, you know, letters recruiting people for this psychology experiment, and said, and basically put people in pairs and said, okay, one of you is going to be the teacher and one of you is going to be the learner. Oh, mind you, the experiment was also completely rigged. There was actually it was pairs, but one of the pairs was an actor, was one of the other psychologists, and he was just pretending, and they would rig, you know, the randomization so that the experimentee was always the teacher and the actor was always the learner. And they put him in a separate room, and he would basically just act out his part. And the idea is that we're going to ask you as a teacher, you ask him questions, okay? And every time he gets one of these questions wrong, you shock him. You push this button, and it delivers a small electric shock, but it grows in voltage as we go on until, as you can see, at the end of this, it's labeled, you know, permanently harmful, and then you've just got like big X, you know, with the death symbol on it, right? And they basically surveyed their psychology class and said, okay, how many people do you think are gonna go all the way here, right? The idea here is that you know, if they get uncomfortable, we're gonna tell them 4 times that, you know, please continue with the experiment. You've got to continue with the experiment. It's imperative that you continue with the experiment. You have no choice. You must continue with the experiment. And after that, they would stop the experiment if they basically resisted if they wouldn't do it 5 times, right? If they so the question was, how many people went to the very end? And the answer is way more people than you would expect go to the very end and deliver a lethal shock to the experiment and to the experimentee. That's what Stanley Milgram is known for. The experiment has been replicated numerous times with fairly consistent results. I mean, the big thing is that it's a person of authority telling you to do something, and you're in a situation where you feel like you have to do something. Now, granted, that's not to say that people turned into heartless killers. Most of them were shocked and had like you know, they were shaking, they were shivering, they were jittering, they had a huge emotional response to it. Such an experiment cannot be done these days because you're essentially really emotionally harmed. You're telling this person essentially that they're killing somebody. So most review boards do not let these kind of experiments get replicated these days because of the psychological harm that it can do to the experimentees. The 50s were a different time. However, a depressing number of people go all the way. That's what Stanley Milgram is known for. Lesser known, though, is the stuff that I used for my research, which was, you know, when you look up psychologists, they sometimes do weird things that deal with computer science. So, Milgram was known for his other experiment, which was the small world network experiment, which was much more benign. Which was basically, you know, everybody's had that coincidence of like, wait, do you know Joe? You know, he lives in New York and he works in a bank and he's like, oh yeah, I know Joe. He's my, you know, I see him all the time, right? You know, just the random connections like that. Those happen, you know, there's 1 in a million chances that seem to crop up 9 times out of 10, right? So that's the other kind of thing that he's known for. And what he did is that he sent out essentially he sent out letters to people and said, that he recruited in this experiment. These were people in Kansas, and said, here's a stockbroker in Boston. Okay, if you know this person, send him this mail directly. If you don't know this person, send these instructions and this packet of envelopes and stamps to the person you think most likely to be able to send him this letter. So, and basically the question is, how many forwards did this typically take? And the answer was 6, because 6 degrees of separation, right? That was kind of where it came from. So, and this is for the packets that were able to be completed, which was about 40% of them, because a bunch of people just gave up and didn't bother forwarding it. You get a random mail as part of an experiment that you never even signed up for, right? So, another thing that you might have trouble signing up, getting the review board to sign off on these days. But the experiment showed that basically you had a bell curve and landed on 6 degrees of separation, and that's because in networks of people, your networks of people, chasing back to this original problem, looks like this, right? I don't need arrows actually here. The relationships people know each other are bidirectional, right? You know these people who are close to you, and they know people who are close to them, right? So it's kind of like a lattice over here, right? But also people tend to have like a bunch of random just hops to other people, right? Just a random hop in some distance. Like I don't know this person in Boston, but I know somebody who lives, and I'm from a small town in Kansas. Of course I don't. But maybe my bank, since he's a banker, maybe my banker knows other bankers, right? So maybe I'll send a letter to my banker, and then he forwards it to some banker he knows in New York, who forwards it to somebody in Boston, right? And so on and so forth, right? The search space shrinks dramatically. And you can end up, and this ends up being like a kind of very weird thing, a very interesting thing in a network where basically every node knows 4 other nodes, and it has like one random connection that's like randomly that follows a specific random distribution. To get from one point to another, you can actually get your routing time can actually look like this: O of log n squared, log base 2 of n squared, which is pretty fast actually. Like even though the square goes quickly, this doesn't. So when I see this problem, I'm kind of assuming like this breadth first search thing. Sorry about the huge aside, by the way, but it's interesting. Now this one is the if I'm assuming that this has like a lot of branches in this one, I'm assuming I'm going to go with the breadth first search because I feel like that one's going to get me there. Now, how would I actually find the optimal path in a really good amount of time? That's actually an interview question that I've seen before, or at least a practice interview question. And the key is actually to find the optimal path between these guys, is actually to do breadth first search. But breadth first search takes forever if you're doing it just like from the start to the finish, right? You got to visit my neighbors, which I've got like 100 of, and then my neighbors have 100 other neighbors, which is so 100 times 100 right over there, and then so on and so forth, right? Now, assuming this is a network of people, I can assume that I'm within 6 degrees of separation, right? If this is a network of people. So how can I lower the search space? And it's actually kind of clever. You do a breadth first search from here to here, and a breadth first search from the goal to the start. So you do a breadth first search simultaneously on both ends. So you search all of the start's neighbors and all of goal's neighbors. Is there an intersection? Have you found a node that's similar? No? So continue. Now search the neighbors of the neighbors. And now basically you've done 2 steps in either direction, but really it's 4, right? And then you can do 3 steps in either direction, and now you're searching the neighbors of the neighbors of the neighbors, right, in both directions. But in reality, you've searched my neighbors, the neighbors of the neighbors, the neighbors of the neighbors of the neighbors, the neighbors of the neighbors of the neighbors of the neighbors, and so on and so forth, right? And it's real, and that will get us a collision much faster. Now, of course, this will eat up ginormous amounts of space to do this. So, all right. So, let's go ahead and see what else we've got for you today. So, end result of this long diatribe is that actually, if you're interested in finding some unique problems, look up stuff in other fields like psychology. They research really interesting things, and you're never sure when something might be relevant. So let's go ahead and see that. Did we go over this problem in class? I think we did. Yep. So let's see. I think one thing I want to go over again is quicksort, because even though that's not like, how do you perform the partition function of quicksort? Let's review that again, because I know that's going to be on the exam, right? So I know it's going to be on the exam because I wrote it. So So let's go over, let's come up with like a random kind of quicksort kind of a random unsorted array. So 1, 2, 5, 7, 12. Let's go with 15 here. Actually, let's go with 13, 30. 100, 1, 3, and sorry, we already have a 1, so 30, 3, and 4. Okay? So how does this work again? Well, now on the exam, you're only going to do one layer of quicksort, only one run of the partition function. So essentially, getting it so that it gets partitioned into the pivot, everything less than the pivot, everything greater than the pivot, and then putting the pivot in the middle, right? That's all. So you're only going to do one layer of this. You don't have to quicksort the entire thing. You just got to do one layer. So to do that, right, how does the partition function work? You have our pivot, which is the first element of the array or subarray we're trying to do, and then you have the last element over here, right? And you travel up the array, right, looking for the first number that's bigger than our pivot, and then travel down for the first number that is smaller. Okay, so let's travel up the array looking for the first number that's bigger than 13. 2 is not bigger, 12 is not, 1 is not, 7 is not, but 100 is. Now we travel down the array looking for the first number smaller than our pivot. Well, we found it. It's down. Sorry, it's right over here. So now up and down haven't crossed, so we're going to swap the values of up and down. We're going to put 4 here and 100 here. Now continue. We look for the first element that's bigger. Look for the first element that's smaller. They haven't crossed yet, so we separate it into up and down, so 3 and 30. Okay? And now we look for the first item that's bigger. Look for the first item that's smaller. And now they've crossed, so we don't swap them anymore. What do? Remember, when they cross, that means that we've partitioned it successfully into 3 portions. The pivot, all the stuff that's less than, all the stuff that's bigger than. But what we want to do is put the pivot in between those 2 sections. Easiest way to do that is that we actually have a reference, we have the index of the last thing in the smaller section, right? So we can take that and swap it with the pivot. So now if we do that, we swap 13 and 3. We end up with, this section that's smaller than the pivot, and the greater than. And this would be your answer on the exam. Remember, it's not fully sorted. We're just doing one layer, right? Because doing recursion because once you start going more than one layer deep, and you start getting into the flow, it's easier to make mistakes, right? We're trying to avoid as many careless mistakes on the exam as possible, right? That's also why it's a good idea to show your work. So if you need more space and the spacing on the exam is a bit weirder, just because I had to do it as a Word document. I'm working off a template that we've been using for a while, so you'll want to, if you need extra space, ask for a sheet of paper or bring some extra paper with you and just attach it to your exam, like fold it in or something. It's pretty easy to put your work in with the exam, and I'll take a look, and I'll be sure to take a look into it or take it into account. Okay. So let's see. So Okay, so I've got 10 minutes left, but I feel like I've done a pretty good and thorough review of all the material that you've got. So, any questions of specific like problems you want me to go over in the last 10 minutes? Are there any like specific instances of problems? Most of the exam problems deal with trees and linked lists. Okay. Right. And I just want to remind you, since it's been a while since you dealt with linked lists, remember, linked lists have items in them, but the items don't have a dot next, right? Okay, it's the nodes themselves that have a dot next in them. Okay, that's one thing. Next thing, the other big thing to note that people, I just get really irritated when I see this on exam because it generally accompanies a very bad answer, is when somebody, we have a linked list L1 or something, right? So we've got L1, linked list L1, and people do L1 dot next. Okay? Don't do that because it's a linked list. It's not a node. It doesn't have a next, right? Linked list, that's like saying, I can't actually think of an array equivalent of it, to be honest. But it's basically saying that here we want to do, we want to get the next node, I know what you're trying to do, right? And a lot of times you don't a lot of people also do the whole head while head does, while head is not equal to null kind of deal and essentially remove stuff from the list. That's generally unnecessary. To iterate through a linked list, just use a for each loop, right? Right, to iterate through a list, if you need to iterate through a list, you can do for, and this works for both array lists and linked lists and sets. And tree, it works for everything. Although for a tree, I don't know what order it would be in. So you'd have to tell me what order it would be in. So for basically E item, a lot of the questions will assume that that integers are what's stored in your nodes. But so if that's the case, use integer int instead. But for L item in your list, right? And there you don't even have to worry about next, the next or previous or whatever. It's just going to go through. It's going to go through your linked list, right? That's something to keep in mind. Okay. Remember your functions. Otherwise, it's fairly straightforward. People have asked me also what they can bring as notes since it's open note and open book. Like, can you bring out can you print stuff out? Can you type up your notes and print them out? Yes. Can I print out pages from the textbook? Yes, because you can also bring the textbook, so that's no problem. Can I bring my previous exams from this class? Yes. Can I bring the previous exams that my friend gave me from other semesters? Probably not, because they're not yours. That's kind of a murky area, and I'd rather not have to make a weird call about that. Okay. Can I bring in basic, but anything else, like, so long as it's like paper, you can bring it in as a note, right? No, you can't bring in you got to, look, when it comes, if it's made of paper, then we'll go, without electronics baked into the paper, so yeah.
Can I print out every page of Stack Overflow?
I mean, you probably need you need a wheelbarrow to bring it in. Sure. Yeah, if that's a note, it's on paper, right? The big thing is that, right, a big part of being a computer scientist is knowing where to get your information from, right? The same thing applies if you're IS&T. Being able to know where you need to get your information and being able to use it in a successful manner. So bringing it in, anything you want, is perfectly fine. That said, it's possibly not in your best interest to go overboard with that. Preparing for this exam the same way you prepared for my two exams, where you bring in a single cheat sheet front and back, is possibly the best way to go, because you'll basically be able to prepare your stuff on that sheet. It will help you refresh your memory of that stuff, and then you'll bring it in as an index basically for all your other notes. So if it's not there, it's sort of like a cache. Right, if it's not in your cache, your first page, you can look at all the other stuff. And so, so and that will be able to be helpful for you. So it's the open, you only have 2 hours, so having a textbook and trying to flip through the textbook for every answer could be a hindrance. All right, so I'll see you guys on Monday, and we'll figure out something to do. You also have lab as usual on Friday. You don't have a new homework. Be sure to demo your stuff.